So once you figure out the tool or the instrument or the method that you want to use to analyze your sample or process your analyte, we can think about the processes in sort of like a block diagram, a really simplistic way, right? You've got your instrument, this black box essentially, which it won't hopefully be complete black box after this class, but certainly after you take Chem 342, you'll learn all about what's on the inside of this thing. You put your sample into it, right, and you get some response out. And you hope, as I mentioned before, that the response is linearly correlated, but it doesn't have to be. It just needs to increase as the sample concentration increases. But how do we know? So response is this arbitrary thing, right? It could be voltage, it could be absorbance, it could be conductivity, etc., etc., etc. These are physical quantities that we as humans know how to interpret. Most of them have to do with electronics, but if you're talking about an instrument, they don't have to be. So calibration is the process by which we correlate the response back to our sample and the concentration of our analyte. And we do that typically, the process is calibration, but we do that through an algebraic relationship where we relate our response variable, which is going to be y, to our input variable, concentration, through the equation of a line. It could be a straight line, it could be a polynomial, it could be whatever. This process is calibration, right? And that's what a calibration curve is. It's relating response on the y-axis, in whatever these units are, to the input, which is often concentration. It doesn't have to be, but it often is. And so an example would be using this Cary UV-Vis, which many of you may have seen or used. We have several of these things in the department. These are research grade absorbance spectrometers. So we would put our sample inside of here, and based on the concentration of that analyte, as long as it absorbed light in the UV or visible range, then our response, which we would see on the computer, would increase as the X or our concentration increased, right? And we would be able to then generate a response curve, which we also call a calibration curve, where it's response as a function of concentration, and we hope that that's a nice straight line. So this process of calibration, there's a few different ways to do it depending on some constraints of your sample and your system and your time and your resources. So I'm going to go over a few of them. This video is focused specifically on the use of what we call external standards, and this is likely the way, if you have created a standard curve, which many of you should have if you're in this class, you've done it in a Gen Chem or Biochem or something, 99.99% confidence that this was the method that you used to generate your calibration curve. So we're going to, hopefully this will be review, and then I'll introduce two new types that probably many of you have never seen before. Okay, so for external standardization, which is the first technique we'll talk about, let's do an example, which is an example you'll hear me talk about a lot because it's really simple to conceptualize. Measuring a metal ion in drinking water, which is lead, which coincidentally is a focus of one of the many research projects that's running in my lab right now. So the sort of standard way to measure lead ions in drinking water is using this process called atomic absorption, which we have a couple of these in the department. You're not going to use them because we're not going to do this in person, but it actually works just like a UV-Vis spectrometer, but instead of measuring the absorbance of the solution, we actually have to get that ion into the gas phase, and we do that by having a torch right here. We toss in our sample, we inject it, it excites to a higher energy state, drops back down, absorbs light of a particular wavelength, so it essentially operates the same way that a UV-Vis does. It just has this step where we heat up the sample in the middle. Okay, not important that you know exactly how to do that. We'll talk about this actually in week 3 of this class. We'll talk about how this thing works. But in external standardization, if you have a sample, and let's say you've got this sample over here, somebody in Flint gives you a bottle, and this bottle, it's got some unknown amount of lead in it, right? How do I standardize this thing? How do I calibrate my tool, right? Because I'm going to put in, as my input, I'm going to put in my sample. It's got some amount of lead 2 plus in it. And as an output, my response, it's going to tell me the absorbance of that sample. That's my response. So somehow I need to establish a functional relationship, ideally in the form of y equals mx plus b, which is the linear form of that relationship. And the easiest way to do that is to first inject into this instrument known quantities of my analyte, which we call standards, and then measure the response as a function of known input values of x. So what that might look like is you create a set of what we call external standards. External standards, I'll tell you why the semantics of such a name. External standards are just beakers or volumetric flasks that you've prepared of known amounts of lead 2+ in drinking water. So you might go through and make up some, in volumetric flasks, several, these are really bad flasks, several samples. Let's see, how many do I have here? 5 that I want to show you. So you have volumetric flasks, and you make up several known quantities by dissolving a solid or by diluting a higher concentration of a known quantity of lead. And say we'll have one that has 0, or by 0 we mean we're not adding anything to it, because again, you can't have 0 in chemistry. Maybe something that is, it's not that, 1, 2, 5, and 10, and we'll say this is in parts per million, right? Hopefully you have more sig figs than what I'm showing you here, but I'm just showing it for simplicity. So you have these, so we can show this data in table form. So I'll just write lead in brackets. That means lead concentration is 0, 1, 2, 5, and 10, and then we have our response here. So we would take each one of these solutions, right? So every one of these solutions has got some stuff inside of it. We take each one of those and we would inject it into our spectrometer, right? And each time we did that, we would observe a response in units of absorbance based on the tool that we're using. And so say that our first absorbance gives us 0. That's nice, that's convenient. The next one gives us a response of 0.1, and then 0.2, and then 0.5, and then 1. So the reason that these are called external standards is because they are made completely on their own, external or exclusive of our sample, right? So we would measure these standards, and then we would measure our sample. So we've got this sample up here. So now we need to take this sample and we need to inject it into our instrument, but we don't know what the concentration of lead is, right? So I'll add a column here, or a row here, where we don't know for our sample what its concentration is, but we'll say that it measures an absorbance of 0.321. Right? And so now we are trying to determine this unknown value based on the response versus concentration ratio or relationship that we've established there. Easiest way to do that is to generate your calibration curve or your response curve. So this you've hopefully all done before, where you have your response on your y-axis, which in this case is absorbance. You have your input, which in this case is concentration of lead 2+. We would have values of 0, 1, 2, 5, and then we'll say 10 is way out here. And then we have our corresponding absorbances up here. I'm just doing this sort of loosely, but I'll do this in Excel in a little bit. And in this case, I made the numbers work perfectly. So you have this nice exact linear response, right? In Excel, we can go in there and say, hey, Excel, do a linear regression and fit a straight line to all of those points. And then we can say, hey, Excel, tell me what the equation of that line is, and also tell me how well that line fits the data, or in other words, how well those data points fit that modeled line which we use this metric known as Pearson's correlation coefficient, or R² value. And R² of 1 means your data points, those blue points, fit that modeled line perfectly, which is always what you aspire to do. But more often they're a little less than 1. If you go to work for the EPA, the Environmental Protection Agency, on environmental chemical analysis, all of their methods require you to have an R² value on your calibration curve that's in excess of 3 9s and an 8. So you know what to aspire to. Okay, so once you have the functional relationship for this equation, then you can take this absorbance value, which is y, right, in our equation, and you can pop it in for your equation of the line, solve for x, because the slope and the y-intercept will be known from the equation. I'm just putting them as m and b here, but those would actually be numerical values, and you would solve. And in this case, if we just look at this, we don't even need to solve this. We can say, well, if we got 0.321 here, then that would equate to 3.21 parts per million of our unknown. This is external standardization. And again, the reason why we call it external is that the sample is distinctly and discretely a different solution from the standard solutions that we make up. We're making up physically different sets of standards. They're all in their own bottles. They have nothing to do with our sample, and we're running our sample separately. You may say, well, isn't that the only way to do it? And the answer is no, of course not. There's actually ways in which we'll combine these two together in the same solution, and that's what we're going to talk about going forward. So this is the simplest way to do this. What are the pros and cons here? So pros, it's pretty fast, right? It's pretty easy to do, and it's generic and it's general. So it's the way that you learn how to standardize an instrument. What are the cons? Well, the big con here is that it does not account for any difference in the matrix, which we call the matrix effect, between the sample and the standards. What the hell does that mean? Let's go back to this picture, right? When you are making up your standards in lab, which is this set of solutions here, you are taking some amount of lead solid, probably, as, say, I don't know, lead nitrate. So you get that from the chemical stock room, you do the math, you weigh it out into the volumetric flask, and then you fill it all the way up to whatever that volume is in the volumetric flask with pure water, right? So that means the matrix, your analyte is still lead 2+ as it dissolves, but the matrix is pure DI water. Now let's think about if this sample is coming from Flint, drinking water, is it going to be pure lead 2+ with nothing else dissolved in it? Is that what our drinking water is? Of course not, right? There's going to be a whole bunch of other junk that's dissolved in our drinking water. There's going to be a plethora, a whole slew of different other ions. Copper and aluminum, silicates, there's going to be bicarbonate, there's going to be carbonate, there's going to be different buffered acid-base solutions in there. There's going to be a bunch of anions, chloride and sulfate and nitrate and nitrite and all the things that come with natural water systems, even processed natural water systems. There's going to be organic compounds. There's going to be things called halomethanes that come from the water treatment plant. There might be trace amounts of bacteria. There could be all sorts of stuff from people's consumer pipes that are in their house that contribute to that. That's the matrix. Can we safely assume that that our response from our instrument here, the absorbance, is going to be completely independent of all the other junk that's present inside of our sample? Maybe. Sometimes you can, sometimes you can't. For a drinking water sample, that's a pretty clean matrix. So maybe using pure water when you're making up your standards and comparing that to a sample of drinking water, that might be reasonable. You might get away with it. But let's pretend you have a different sample here. What if you have a sample of lead, and this is coming from the sludge that's in the Flint River? Right? So somebody went in and dredged out the Flint River, and they said, well, I want to know how much lead is actually in the sludge there because the Flint River goes right through the industrial heart of Flint, Michigan, right? So there's probably been effluent of lots of different heavy metals over the years that might have sedimented out into that. Now, let's think about the matrix effect, right? Now you have, again, in the lab, you're prepping your standards with pure DI water as the matrix. But in the case of the sludge, you've got all sorts of junk, not just, mud and sand and dirt and leftover boat parts and whatever you have. In that case, the matrices between these two, between your standards and your sample are drastically different. And very likely when you take this sludge sample and you inject it into your instrument of choice, it's going to respond differently simply because of all the other effects from the matrix that may suppress or they may add response. We don't know, but it's not necessarily safe to assume that the response is going to be unaffected by this drastically different matrix. So that's the major con in this type of standardization, is that it's not very good for complex matrices. The other con in external standardization is what we call instrument drift. Drift has to do with how the response in our instrument, how it changes over time. So if you think about the sequence of events when you're standardizing your tool, right? Often you run your set of standards first, so you pop those in, and then you run your sample, and then you're done for the day. Consider you have 1,000 samples to run, right? Maybe you're an industrial lab. Happens all the time. So they run their set of 5 standards early in the morning, and then they get to work on running their 1,000 samples, right? So 8, 10 hours, 12 hours later, they're still running their samples, but they're still relying on the standard response that they got in the morning. That assumes, if they're going to do that, that assumes that the response of the instrument is perfectly the same all day long. It doesn't change ever. That's unreasonable. You think about this is a physical electronic object. This has got a flame in it, right? The flame is probably going to change in its hotness between the morning and the evening. It's going to assume that the detector inside of this thing doesn't change over the day. Maybe this thing's in a room where the sun hits it, right? So in the morning the sun's not hitting it, and then at noon all of a sudden it gets direct sun. That detector starts to heat up a couple, 3 or 4 degrees more than it was before. That means the response starts to rise too, and the whole thing starts to drift over time. This type of external standardization does nothing to compensate for the drift of our instrument. And so that's the second con of this type of standardization. So we need maybe something with a little bit more finesse to compensate for more complicated samples or samples where we expect the instrument response to drift over time.